Hey everyone, and welcome to The Explainer. Today, we're going to tackle one of my absolute favorite sorting algorithms. It's super elegant, super reliable. It's merge sort. So, have you ever wondered how a computer can just reliably sort millions of things in the blink of an eye? I mean, think about it. Your emails, your search results, massive data sets. We need sorting methods that aren't just fast, but predictably fast. And you know what? Merge sort has an absolutely brilliant answer for that. All right, so the secret sauce behind merge sort's power is this classic strategy: divide and conquer. Seriously, think about it like you're trying to solve a huge 1,000-piece puzzle. You wouldn't just stare at the whole messy pile, would you? Of course not. You'd break it down, right? You'd find the edge pieces, then maybe group sections by color. You make the problem manageable. That's exactly what we're doing here. Okay, so what does divide and conquer actually mean in a more formal sense? Well, the idea is that merge sort takes a list and just keeps recursively breaking it down into smaller and smaller pieces. It keeps going until each piece is so tiny it's already sorted. And that makes sense, right? A list with just one single item in it is, by definition, already sorted. From there, it just masterfully combines these tiny, sorted pieces back together. So it really all boils down to this simple three-step process. First, you divide. You break everything down as far as it can go. Second, you conquer. You start merging these tiny little pieces into slightly larger, now sorted pieces. And finally, you combine. You just keep repeating that merging process over and over until, boom, you have one single, perfectly sorted list. Okay, theory is great, but let's actually see this thing in action. I like to call it the merge sort dance because it's just this series of really predictable, kind of elegant steps. Let's walk through an example and you'll see exactly what I mean. So let's start with a really simple, unsorted list of numbers. We've got 3, 2, and 1. Our goal here is to use merge sort to get them into the right order. 1, 2, 3. All right, first up is the divide step. The algorithm is going to split our list in half, and then it splits those halves again, and it keeps going until we're left with the smallest possible units. In this case, that's 3 individual arrays, each with just one element inside: a 3, a 2, and a 1. And like we said before, these are now trivially sorted. They're sorted by default. Now for the fun part, the conquer phase. We take 2 of those adjacent arrays, the 2 and the 1, and we merge them. So how does it do that? Well, the algorithm looks at the first element of each, and it sees that 1 is less than 2. So 1 goes into our new array first. Then 2 just follows right after. And the result? A brand new sorted array, 1, 2. And for the grand finale, we perform the last merge. We take our one remaining array, the 3. Pretty cool, right? That whole visual dance we just watched is exactly what the code is doing under the hood. So let's connect what we just saw to the actual functions a developer would write. So the code is usually split into 2 main parts. You've got the merge sort function on the left, and that's the one handling the dividing. See how it calls itself twice? That's the recursion we were talking about, the part that breaks the array down. Then it calls the merge function over on the right. And that function does all the heavy lifting of conquering, comparing the elements and combining the pieces back together. Okay, here's a little pro tip, a really crucial detail you'll find in the source code. When the algorithm is finding the middle of the array, instead of just doing left plus right divided by 2, you see this slightly different formula. Now, why on earth would they do that? Well, with really large arrays, just adding left plus right could actually become a number so big that the computer can't handle it. It causes something called an overflow error. This simple change completely avoids that problem. It's just a super clever, robust little detail. So we get how it works now, but the bigger question is, why would you actually choose it? Because every algorithm has its own strengths and weaknesses, right? So let's dive into the performance and the trade-offs of merge sort. This right here, this is the big one. Merge sort has what's called a time complexity of O(n) log n. Now, what that actually means for us is that its performance is incredibly consistent and super efficient, even when you're dealing with massive amounts of data. And what's really crucial here is that this is its worst case performance. That is a fantastic guarantee to have. No nasty surprises. But, there's always a catch, right? There's always a trade-off. To do that merging step we saw earlier, merge sort needs some extra workspace. It needs a temporary array to hold the sorted values before it copies them back. And this means it uses extra memory, what we call O of n space complexity. Basically, it needs extra space that's proportional to the size of the list you're sorting. And this table really puts it all into perspective. Just look at something like Quicksort. Yeah, it's fast on average, but its worst case scenario can be pretty terrible, O of n squared. Or Heapsort, which uses way less space, but it's not stable. And stable just means that if you have two equal elements, their original order is kept after sorting, which can be super important sometimes. Merge sort really hits that sweet spot. You get that guaranteed O(n log n performance, and it's stable, all for the price of a little extra space.
Okay, so a truly great algorithm has to be tough, right? It needs to be robust. It can't just work on nice, simple examples. It has to be able to handle all the weird, tricky inputs you could possibly throw at it. So let's see how merge sort holds up when we really put it through the gauntlet.
So, what about those edge cases? You know, the situations that can really trip up other, lesser algorithms. Does that core logic of divide and conquer still hold up when things get weird? The answer is a resounding yes. It handles it all. An array that's already sorted? No problem. It just performs a bunch of really simple merges. A reverse sorted array? The logic works exactly the same. What about duplicates? It handles them gracefully, and because it's stable, their original order is preserved. Negative numbers, single element arrays, even empty ones. The recursive logic just handles every single case perfectly. It's just incredibly reliable. And that really brings us to the core question here, doesn't it? Merge sort makes a very clear bargain. It uses a bit more memory in exchange for absolutely guaranteed, stable, and predictable performance. So the real takeaway is this. In a world that's full of variables and uncertainty, when you absolutely positively need your sorting to be reliable and fast every single time, is that trade-off for extra space a price worth paying? For a lot of critical applications out there, the answer is a definite yes.